You're looking at something that I think is just fantastic. This is a visual representation of the proportions of square root of 1 and then continually adding 1, square root of 2, square root of 3, square root of 4, square root of 5. And you can continue this pattern infinitely, really, if you could do that. I'm going to explain how we construct this with the compass and straight edge, but if there's interest, I could actually demonstrate that. I'll just give a basic overview. I'll show you some other versions of it, but basically if we count the radius of the first circle as 1, the next circle has a radius of radical 2, then radical 3, radical 4, and I'll explain how we can even prove that and show the proof of it mathematically using the Pythagorean theorem. At the end, if you're interested, I'll also show you how to do this on the Geogebra software. So this is what it would look like if we took out the guidelines and printed it out from Geogebra. And I don't know why, I just love the way this looks. It's quite interesting to me. If we took out the squares and added some color, it would look like this. And if we took away the colors, it would look like this. So we're seeing visually the size of these circles are the pattern of the square root and adding 1 to it. Square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, square root of 6, and so on. I believe this one's up to the square root of 27, which is 3 radical 3. I'll also show you how if we go inward, we could get radical 2 over 2 and keep going that way if we wanted to as well. What it is we have these, we start here, so you could even see the angles that are formed. And one thing that I find striking visually is that you can see that the difference between each preceding square root is less and less. So the distance from square root of 1, which is 1, to square root of 2 has this gap. Then to square root of 3, it's a little less, then a little less, a little less. So the difference between each square root, we can see visually the proportion, but we could see how it becomes less and less and less. We want to be sure we're familiar with the basic math of the Pythagorean theorem in order to do this. So I've always found it fascinating that square roots that are not perfect squares are an infinite decimal, kind of like pi. So we take the number pi, and it's 3.141, and it's a decimal that just goes forever, and it doesn't repeat. And really, as a proportion, we can show what this means, but we can't really fully write it down, just like we can't write infinity, but we can talk about it. So the number pi comes from the distance around a circle divided by the distance across the circle going through the center, the diameter. So it's how far around the circle divided by the diameter across the circle. So, you know, in many ways, these infinite decimals are really magical, and yet in another way they're not. For example, think of 1/3. 1/3 is 0.33333 because you can't fully cut it into a decimal that doesn't ever end. However, this one repeats the same number, and the square roots that are not perfect squares, like square root of 4 is 2, it's a perfect square. Say square root of 2, it's 1.414, and it continues, but it doesn't repeat. It doesn't have the same repetition here. So I have always found it fascinating that we could visually represent a square root, but we can't write the infinite decimal. So the Pythagorean theorem, it says that when we look at a right triangle, the sides A and B, which are the two sides touching the right angle, the 90-degree angle, a squared plus b squared, when we square them or multiply it by itself, it will equal the hypotenuse, the one across from the 90, or c squared. So for example, when we saw the square we had with sides 1 and 1, if we ignore this and we want to find c, we would say 1 squared plus 1 squared equals c squared. and so c would be radical 2. I do have a video on the Pythagorean theorem if you wanted to brush up on that. Essentially, to create this design, we start with a circle. And we cut the circle in half by going through the diameter, and then we cut that in half. Now we have that square that we put around on the tangent points, meaning it's touching one spot on the circle. Now, what we had shown a moment ago about the Pythagorean theorem is if this radius is 1 and 1, then from here to here is 1 also, and here to here. So this creates for us radical 2. So we know that this blue line represents radical 2. Then you'll notice another circle goes around it. And so in order to continue to find the next square root, we drew these lines and extended them. This blue line shows us that we have the radius of radical 2, so anywhere around touching the circle is radical 2. This would indicate that from here to here, we have radical 2. Because the radius is 1, from here straight up perpendicular to the line is also 1. So we are going to form another triangle here. I'll use an let me use a different color. Let me use purple. This purple right triangle now is going to have square root of 2 as the base and 1 as the height. So what we end up having now is the ability to use the Pythagorean theorem to find that purple circle. That purple line, and then we'll turn it into a circle. So if the bottom is radical 2, and if the height is equal to 1, we can find this purple line using the Pythagorean theorem. 1 squared plus radical 2 squared is equal to c squared. Now a radical times itself. Radical 2 times radical 2 is normal 2. So we have 1 times 1 is 1, plus 2 is c squared. We're going to get c squared is equal to 3, and then we square root both sides. C is equal to radical 3. So this new line that we drew, which is purple, is equal to radical 3. We'll use our compass to then draw another circle. And now we know anywhere touching that purple line to this and connecting to the center is radical 3. So from here to here, we know is radical 3. And we're going to repeat this process. So we know once again that the height is going to be 1. So it creates another triangle. Now the bottom is radical 3. The height is 1. And doing the Pythagorean theorem, we're going to get 3 plus 1 is 4. So now we know this new line is 4, or radical 4. Let me use another color. I'll use green to represent it. So from here to here, this green hypotenuse is radical 4. If we draw another circle all the way around it, we know everywhere touching that circle is radical 4, which means from the center to here, I'll draw it underneath so we can color it, is radical 4, and again the height is 1. Like we said, if we take this shape and we zoom in to here, we're looking at this square. And so that first circle, this first circle has a radius of 1. 1. And these guidelines show us that this amount is 1, this amount is 1, this amount is 1, this amount, and this amount, and so on. And we're going to use that. So that's 1. However, this is 1, this is 1, this is 1. All of these are the same as the first radius. Now a radius all the way around a circle is the same distance, so we know that this is 1 as well. So we're going to find this hypotenuse, which we just showed, and it's going to be radical 2. So this spot here to the center is radical 2. Now we use a purple marker, or we used a purple ink on Geogebra. Oops, that's not purple. And basically this purple line is radical 2. So if we make a circle with that as its radius, any line that touches this purple circle connecting to the center will be radical 2. This means from here to here is radical 2. And remember, going straight up, we know it's 1. So we didn't have, let's pretend we don't have this point yet. So what we did is we make this perpendicular line. And so we're going to show that from here to here is radical 2, which is going to prove that this is radical 3. So this orange line we're going to show is radical 3. Let me show you what I mean. If we draw the bottom, which is radical 2, and we know that going straight upwards is 1, finding this orange line that creates this right triangle can be found using the Pythagorean theorem. So 1 squared plus radical 2 squared is c squared. Now radical 2 means radical 2 times itself, which is normal 2. So any square root times itself is just that whole number. So square root of 2 times square root of 2 is normal 2. 1 squared is 1. And so now we have c squared is equal to 3, or c is equal to radical 3. So this orange line is radical 3. So from here to here is radical 3. Now, if we make a circle, which is already made here, using that amount, we know every distance touching that circle to the center is radical 3, which means from here to here now is radical 3. And remember, going straight up is still 1. So we're going to show using the Pythagorean theorem again how the next line, this blue line, is equal to radical 4. And so each of these is 1. So when we're making our Pythagorean theorem, if you notice that pattern, it's continually adding that 1. So for example, let's go to square root of 4 squared plus 1. We're going to get 5, or the square root of 5. When we do the next one after that, we're going to use 5 plus 1. So we're going to get the square root of 6. And then we'll use the square root of 6 plus 1. And then we're going to get square root of 7. So we're going to continue that pattern, and really using the Pythagorean theorem, you can prove that each of these hypotenuses, I'm not even sure how you say multiple hypotenuses, are going to be, as we go forward, one more than the one before it, one more than the previous. So we start with square root of 1, or 1, then square root of 2, square root of 3, square root of 4, square root of 5, square root of 6, square root of 7. And so in a moment when we take a look at the digital versions that I printed out, because they're a bit clearer, we can remove these lines and just look at the circles. So we're looking at these circles that are a pattern of square root of 1, square root of 2, square root of 3, and continuously. And really, if you want a computer generator, you could go as far as it would let you. So we can check our compass to see if radical 4, which is 2, is twice the distance of the radius. 2 times the distance. Now, if we continue this pattern, this was radical 4, radical 5, radical 6, radical 7, radical 8, radical 9. So let me use green. This spot from here to here represents radical 9. So this green circle has a distance of a radius of radical 9. So here to here is radical 9. And we know that radical 9 is the same as 3. So let's check. 1, 2, 3. So I think this is, I don't know, there's just something really neat about it. You can see visually the ratio or proportion. Really, it's the proportion of the radius. But you can also say the diameter, right? The diameter of this line could be considered 1. And then the diameter of the second circle would be radical 2. The diameter of the third circle, radical 3. And you can continue so on and so forth. You can see the distance between each one gets less and less and less. It's something I never considered. So, you know, the distance between radical 2 and radical 3 is much more than the distance, say, between radical 26 and radical 27. It gets to be less and less as you go. So, hopefully this made sense. Another version of this is, what if we actually connected each hypotenuse and continued the line, and that would give you the angles. So this is what the angles would look like as we progress each square root. And it starts to almost fade together. You could zoom in on Geogebra and they wouldn't be touching, but they start to look like they're touching. So you could see the angle of each. So we're looking at, basically, if we draw a right angle. So to recap, each of these square roots has a circle with that radius, and we use that as the bottom leg. And then the height of our right triangle is always 1. And so if we took these lines and extended them and continued them and got rid of these guidelines here, we'd show up with this picture. And you can kind of see the way it looks. I almost think we should do the same thing this way and see what that would look like. I think it has a cool look to it. So, you know, we could also ask what's going to happen if we go inward? And what if we drew another square here? Could we find that? Now, because from here to here is 1, we would be missing these 2. So let's do the Pythagorean theorem and see what we get. Using the Pythagorean theorem for this right angle here, right triangle, we have x and x, so we're not looking for the hypotenuse, we know it's 1. We'd have x squared plus x squared is 1, 2x squared is 1, and we divide it by half to get x squared alone. Finally, we would square root it, which is 1 over square root of 2. And as we know, we rationalize because we don't allow square roots or infinite numbers to be on the bottom or denominator. We're going to get square root of 2 over 2. So this particular side here is going to be the square root of 2 over 2. And we can keep going backwards. Now, at the same time, we could just change this slightly and make the second one 1. And then this first circle would be the square root of 2 over 2. So we can go backwards and work with fractions as well. But it's, again, to me, something just very visually stunning. So I hope you enjoyed this cool little look into a really fascinating geometry construction, simply using circles and squares and these lines that are parallel to the center line that are the distance of 1. Down here is the distance of 1. And again, we can continue this as far as you're willing to go, whether it's using your compass and your ruler or using Geogebra or a math software. So I hope you enjoyed it, and if you have any questions, please leave them. And if there is some interest in showing how to construct this, I'm willing to do that if somebody would like to know. I saw this somewhere, and I happened to draw it and write it down a while ago, more than a couple years ago. And I actually wrote it down wrong. So I was looking at it at the time, I kind of didn't understand it. And then it turns out I was drawing the squares in the wrong place. So thankfully I did go back to it. But unfortunately, I don't know what to look up and what words to use for a search to find that YouTube video. I'd like to give the person some credit. And, I didn't really truly understand the explanation at the time. So I know this is a little bit math intense, but for those who could understand it, maybe you're thinking it is a little bit as cool as I do. So you all keep learning geometry. You'll learn new things all the time. So for those really dedicated, I'm going to show you how to use Geogebra software to create this design. And I'll keep the grid lines on. We can always remove them later. We're going to start with a square. So I'm going to go down to where the regular polygon, regular means each side will be congruent or the same. I'm going to click 4 vertices, 4 sides. And what I'm going to do is put a circle in the middle there. So the grid lines are going to help us to see the middle. And I'm going to touch the middle and then touch point C where I want the edge of the circle to go. I'm also going to do that again from point E and go right up to the top of the square. So it's touching each of the edges or a tangent to the square. So what we said was from E to F represents 1. So let's make E to F make a segment. And then from E to C, it will represent radical 2. And we can always color these as we go or at the end. So I'm going to touch FE and make it red, and make the circle with that radius all the way around will also be 1. I'll make it red as well. So then I could touch EC and make it blue, and that represents radical 2. And I'll touch the circle that has a radius of radical 2, or the square root of 2, and I'll make it blue as well. Next, we just need a few guidelines to help us with the construction. So I'm going to click the line tool and make a line from D to C and a line from A to B. But I also want one in the middle, so I'm going to go from the very left side of the semicircle to the other side. If you want to zoom in, you could make sure you're really accurate. Just like with a compass, you want to be accurate. So next, as we said, the distance to that blue circle is radical 2. So we want to go straight up at that blue spot here where my mouse is. And I'm going to use the perpendicular line tool to help us find that spot, and we'll use that over and over again. So I'll click the perpendicular line tool, and I'm going to click the line DC and then shift it over until it touches the blue circle. So now we have radical 3. We found that new spot. I'll use a segment to go from E to that spot, J. And we're just going to keep repeating that process. From E to J, we draw a circle. And if we'd like, we can color it. So let me make it orange. And I'll make the circle orange as well. Let me move this where I can see it. There we go. So now we're going to continue the same exact process. There's these couple of steps. I'm going to make another perpendicular line. I'll touch the line that goes left and right from D to C here, And then it allows me to find the perpendicular line and put it at the spot I'd like, and I'll put it on the orange circle. And then now right above it here we have radical 4. So I'll take my segment and connect it to radical 4. And then again I'll make a circle of that radius. So I'll click E and then click L. And again we can color it if we'd like. So we know all the way around where it touches green is going to be radical 4. And so we can continue that process over and over and over again, however many times we want. Like I said, I went 27 times, and I showed you some of these examples. I just removed the lines and the guides. So the way we do that is you can click on the lines, for example, the parallel lines we use and the perpendicular lines. And if you want to click on multiple ones to make it faster, you hold down the control button and you just touch each of the lines you want to hide. And let's say I want to hide, oops, I unclicked it. I'm going to hide the parallel lines and the perpendicular lines. Then what we're going to do is touch the 3 little buttons. It's off key here, it's right here. And click Settings. And when I unclick Show Object, they're going to disappear. So I can do that with these points as well. I can click down on it, click another one, click another one, click another one, and then unclick Show Object. So if you're interested in actually making this shape, that'll get you started, and good luck to you.